All right, hi everybody. So we are going to talk about titrations today. Woo! I'm sure a lot of you have seen videos of titrations all over TikTok and Instagram, and you're finally going to get to do one. So in order for us to be able to start this lab, there's a couple things we got to think about. So number one, we've learned a lot about solutions, acids, and bases so far in this unit. We learned how to calculate concentration or molarity of a solution. We learned how to dilute a solution to a new concentration. We learned how to make solutions in the first place, how to define acids and bases, how to recognize acids and bases by their different properties. So the last important skill that's going to come up in this unit is how to experimentally determine the concentration of an unknown acid or base through this process called titrations. So that's kind of really the key to this lab here, all about the experimental process to determine concentration. So why is concentration so important? Why does it matter for this lab what we're doing? Really, concentration is kind of the most important property of any acid or base, regardless of if it's a strong or a weak acid or base. You learned in your video notes that being strong or weak doesn't refer to like your concentration at all. It's just an inherent property that talks about how much an acid can dissociate or not. So if you have a strong acid, it's going to completely break apart into its ions in solution. If you have a weak acid, it only partially does that. So that doesn't refer to concentration at all. Concentration is about the amount of solute you have that's just dissolved in per liter of solution. So if I say, hey, we're working with nitric acid tomorrow, you might think, ooh, spooky, scary. But if the concentration of that nitric acid happens to be something like 0.1 molar, a very, very, very small number, honestly, it's basically like working with mostly water. So concentration is super, super important. If you spilled 0.1 molar acid on you, no big deal, right? You spill 16 molar acid on you, things are not looking good for you, my friend. So let's say that you're given an acid or a base, but you don't know the concentration of that substance. That could potentially be super dangerous because you don't know how cautious you have to be when you're like handling that solution, right? So to solve this problem, we can use titrations to determine the unknown concentration of our solution. So titrations are really just an experimental process. So how does this process work? Well, in a titration, you're going to react a substance of an unknown concentration, but a known volume, with another substance of known concentration and known volume. So think about why those things might be important. If we know information about concentration, we know information about volume. How are those two things related together? Well, they're related by number of moles. So in our labs, we're only going to work with strong acid, strong base titrations. Those ones are kind of like the easier ones. If you're continuing on to AP Chem, get excited because you're also going to learn how to do weak acid base titrations, which are quite a bit more complicated. So when you're dealing with a titration, there's two solutions you're dealing with, your titrant and your analyte. The substance of unknown concentration is your analyte. You have to know information about its volume, though, in order to make your titration work. So, analyte, unknown concentration, known volume. Your titrant is your opposite substance. So let's say your analyte is an acid. You want to use a base as your titrant. Your titrant is your known volume and known concentration. Okay, so why does this even work? In a titration, you're reacting a strong acid and a strong base. So think about like the types of acid-base reactions you know of. Just straight up strong acid, strong base reaction. Well, that is just a neutralization reaction, which is great. What should you be making in a neutralization reaction? React an acid and a base, and you end up with a salt and water. So we'll do this as an example, right? Let's say I gave you hydrofluoric acid and you reacted it with potassium hydroxide, acid, base. Those two things are going to come together and they're going to make a salt and they're going to make water. So why do titrations work? You're reacting an acid with a base and you're going to be left with a neutral substance in your reaction flask. So you're getting rid of all the acid and instead you're making it neutral water. And if you can mathematically know a lot of things about all the stuff you started with and all the stuff you ended with, and you know this end point where you've made water, you can then solve for the unknown concentration of your solution. So what I'd like you to do, one more thing, forgot about this. So in your solution or in your titration, remember the whole point of this is that you're making water. So if you were to write out the net ionic equation for this, you're taking your hydrogen ions, you're reacting them with your hydroxide ions, and you're making water. So the water part that you're making is the most important part of this titration. Okay, what you're going to do now is you are going to pause this video and you're going to go into your lab packets and make sure you complete part 1, that part of the pre-lab section, but you're just going to do questions 1 through 3 for right now. You should be able to answer all of these. I will just refer to you to your notes packet for question 2B, where we learned how to make solutions. It is going to involve a volumetric flask, so you make sure that you have that somewhere written into your procedure. I would say your procedure should be 4 steps long for that one, for 2B. All right, pause the video, answer those questions, then come back. Okay, hi. We Dora the Explored it, and now we've jumped ahead to the next finding. Actually, that's not Dora the Explorer. I can't remember what it is. Anyway, how will we know when our system is actually neutral? So you've reacted your acid, you've reacted with your base, you know you've made water. But here's the problem. Acids are clear and colorless pretty often. Bases are clear and colorless pretty often. So if you mix two things that are clear and colorless together, you're going to end up with something that's clear and colorless because water is also clear and colorless. So how the heck are you actually going to be able to figure out when you've reached this neutral point and you've made water? We're going to use our properties of acids and bases to help us out. We're also going to make use of indicators, which we learned about in 7.4. Acid-base indicators help quickly identify when a substance is acidic or basic via color changes. So let's think about the acid-base indicators we know that can maybe help us out here. So the most common acid-base indicator is phenolphthalein, or titration indicator, I should say, is phenolphthalein. Because phenolphthalein only has 2 possible colors that it appears as. We also saw universal indicator, which had a whole spectrum of colors. Universal indicator we're not going to make use of, we're just going to use phenolphthalein. So see if you can think back to the properties of phenolphthalein in acids and bases. If you drop some phenolphthalein in an acid, it should be colorless. Hopefully you were like, yeah, Miss Lambert shouted out. Oh, that's totally Dora the Explorer. I'm just waiting for you to yell at me through the TV screen. Anyway, so phenolphthalein is colorless in acids, and in bases it shows up as a really pretty pink, like fuchsia color, right? So if we're doing an acid-base titration and you start with your analyte in your reaction flask, you have to drop in a few drops of your indicator. And when your indicator changes color, that's how you know your solution has finished titrating and you've reached that end point. There's 2 types of titrations, right? You start with a base or you start with an acid. In a base to acid titration, meaning your base is your titrant and your acid is your analyte. So your acid's your unknown here. You're going to drop your indicator into your analyte because that's in your reaction flask. So if the acid is our analyte and we put in some phenolphthalein indicator, that means our solution should start as colorless. Once we have neutralized all of it, it will turn very, very faintly light pink. We saw it be pretty fuchsia when we dropped it into a base. When you know you'll reach the end point of your titration when you see a light pink color, very faint, you do not want that fuchsia. So alternatively, you work backwards. If you had an acid to base titration and you were using phenolphthalein, so now base is your oops, I forgot to change those. So now acid is your titrant and base is your analyte. So now base is your unknown. That means when you drop your phenolphthalein into your analyte in your reaction flask, it should show up as pink, super pink, because you've dropped phenolphthalein into a base. So when you're reacting it down, adding acid and acid to it, eventually it's going to turn colorless when it reaches that neutral point. Okay, so keep in mind, especially for number 4, you're looking for that faint pink color. So what does this actually look like? Let me show you a little video here. So this is someone performing a titration. You can see that the reaction flask is starting as colorless, which means that's acid in there. Our acids are analyte. And as she's adding those little drops of the base, you see that pink color start to flash. The pink is interacting with the base, showing that it's starting to neutralize, right? But it's going back away because overall the solution is mostly acidic. As you get closer and closer to the end point of your titration, meaning your neutral point, your pink color will start to stay around a little bit longer. So that's what she was talking about. Oh, let's see if I can rewind this just a little bit. So right here. This pink color is persisting a little bit longer before it goes back to being colorless. Then, as soon as you're about to hit your endpoint, you add in one more drop. If you add in that last drop and your pink color persists and doesn't go back to colorless, you have now reached the end point of your titration. So you're looking for that very, very, very light pink color that she's got in the video here. This is now signaling the end point of your titration. It's signaling that you have neutralized all of the acid, and the only thing that's left in there is your water and your salt, but your salt isn't contributing to the color. Your salt doesn't matter for this process, just the water. Okay, so that is what it looks like kind of in a video form. This is a picture of it because I wanted to show you this last picture here. Basically, like, how far is too far? If you start adding in your titrant and you're going farther and farther and farther into your titration and you reach that faint light pink color and you think, maybe I could use a little bit more, and you add in too much, you're going to over titrate. Over titrating means you have added too much base to your reaction flask, and now instead of being that nice pink color that's got just pretty much water and your salt in it, you now have over titrated and you've added too much base. Now you've added hydroxide ions to your reaction flask, and it's going to show up as a very bright fuchsia color. So you want to be really careful when you're titrating not to add too much. 1 drop is quite a lot. You can even try adding half drops, and we'll talk more about like that kind of like pro tips I have for you in doing your titrations tomorrow. So this is what it looks like. Okay, now we're going to move on to part 2, your lab preparation. We need to talk about your experimental setup here. So I'm going to go to a lab packet. You can follow along with me. So this is going to be a very different setup for you all because we're working with different glassware. You get one, I think this is the last new piece of glassware you get to work with, which is pretty exciting. So the piece of glassware that you are going to work with here is called a burette. Actually, I think it has 2 R's. Ooh, I don't know. Now that looks wrong. You know what? It doesn't matter. So this is a burette. A burette has graduated marks on it similar to a graduated cylinder, but even smaller. So graduated cylinders, the smallest ones we have, measure every 1 milliliter. A burette does the same thing, but it has hash marks that are even smaller inside of it, allowing you to measure to the 0.1 milliliter. It's an incredibly accurate tool, which is really helpful for you when you're doing a titration. Burettes have this little, what's the word I'm looking for? Ooh, a lever, I guess. It has a little lever down at the bottom that's used to open and close the rate of flow on the burette. I'm going to tell you what this is called now, which is great because you can pause the video and control your laughter there. And then tomorrow when you come in, you're going to be so responsible and mature that you're never going to laugh at this word again. So this is called a stopcock. I'm 14. So the stopcock is like the formal name for the lever. When it is parallel to the burette, so let me draw it out for you so you can see what I mean. When it's parallel to the burette, that means it's open and your titrant can flow through the burette. When it is perpendicular, that means it is closed and it stops the titrant from flowing into the reaction flask. Even when you start to kind of turn it a little bit, it'll start opening it up, which means that you could get some titrant to start flowing through. So you do have to be quite careful when you're opening and closing the stopcock on the burette. So burettes, the nice thing about them is that they flow down like this, which means your solution is going to flow down like this. So it would be kind of hard if this were your 0 mark, because you can clearly see that there is solution that's below that you're not taking account for. So a burette actually reads upside down, kind of. This is the 0.00 milliliter mark. So what you do with a burette is you fill it completely to the top, you fill it to 0 milliliters, and then when you open the stopcock and it starts flowing through into the reaction flask, you basically just count upwards to see how much you've used. So let's say at this point, I'm just going to put a random number down, that this number reads 20.24 milliliters. That means that you've added 20.24 milliliters of your titrant to your solution. So this is still just the change in the volume, but you take your final reading and minus your initial reading, final reading minus your initial reading, which is easy because your initial reading is going to be 0 because you filled it all the way up to the top. So burettes, completely accurate. The hash marks are read to, so hash marks every 0.1 milliliters, which means your accuracy needs to be read to this decimal. So make yourself a little note of that so that way you can be as accurate as possible when you're doing your lab. Okay, so burette, that's your new piece of glassware that you're working with. We are still going to be using a ring stand to hold our burettes to, but we're going to use a special clamp to put them on there, and this is called a burette clamp. Wow, burettes use a burette clamp. Incredible, crazy. And then down here, this is going to be your reaction flask. Your reaction flask can be a lot of different things, but we're going to use Erlenmeyer's. Specifically, you are going to use 250 milliliter Erlenmeyer's. You don't need to write that in necessarily. I'm just telling you so you can kind of envision this in your head, what it's going to look like. And then there's a couple things that are not in this picture that we are going to use actually. You want to make sure that you're constantly stirring your the solution in your reaction flask, because you want to make sure that as you're adding your titrant to your analyte, it's really getting mixed in there, especially with the phenolphthalein, and making sure that everything is pretty even, right? So we are going to make use of our little stir bars and our stir plates again to kind of help us out with this. So I'm just going to add that in, stir bar and plate. Okay, so this is your experimental setup. This is what we're going to deal with when we actually collect the data in your lab. So I talked you through what's actually happening in a titration, but we need to make sure you have it written down so you can kind of understand really why this works. It's really important that you understand why this works. So I know you probably feel like I'm beating a dead horse here, but I need you to understand it, so we're going to go through it again. So if you start out with your solution like this, the analyte is clear inside your reaction flask. This is exactly what you're going to do in your lab. Your analyte is also going to be some sort of clear solution when you have phenolphthalein in it, which means you are going to have an acid as your analyte. So at the starting point, inside your burette, you'll have your titrant, what you need to add to your analyte. So inside here, you're going to have your base. So remember from the net ionic equation that we wrote out earlier, what's actually reacting in your base to make your water is the OH minus, the hydroxide ions that are in there. So your hydroxide is going to be a part of your base. I'm going to write it like this just to make our lives easy. Okay. So inside your reaction flask now, you have your phenolphthalein that you've added. And then, so inside here you have your indicator. And you have your acid for our purposes, but it would just be your analyte, whatever your analyte is. So you have your indicator and your acid, and remember what's actually reacting in your acid to help make your water is the hydrogen ions, the H plus ions, right? So I'm going to draw a bunch of H plus ions in here to kind of help us model it out for what's going on in your titration, and we're going to change this over time. So at the starting point, in your reaction flask, only your dissociated acid is present. And remember, we're only doing strong acid, strong base titration. So since this is a strong acid, it's completely dissociated. So we can write a little chemical reaction equation to help us visualize this. This is our general acid formula, where H represents the H of the acid that's going to pop off, and the A represents whatever is left over of the acid. So this strong acid is going to completely break apart into H plus ions and its conjugate base, whatever is left over. Okay. So, and just to make it super clear, strong acids dissociate completely. And that's why we can write it like this. Okay. This is before anything has happened with our titration. Now we're going to start slowly adding in, drop-wise, our base. So our base is going to start flowing through the burette into our reaction flask. And what's going to happen as soon as that base hits that acid? It's going to undergo a neutralization reaction. So base will start to neutralize acid. So what does that really mean? It means we're making water. So base will start to neutralize acid. Water is made. So what's going to actually happen to the acid? So the concentration of our acid will start to decrease, or the concentration, I can say, of our H plus, because that's really what's going to react here. So concentration of H plus is going to go down as the H plus and the OH react to form water. Okay, so the reason why it says slow down here is just to remind ourselves that that pink color is going to hang around a little bit longer as you start getting closer and closer to the ending point of your titration. So at the end point of your titration, you have this persistent pink color that is left over. So what should this mean? It should mean that all your acid has been neutralized. So all acid is neutralized. Only water and salt are present. So what this is helping us understand is that the moles of the base that you've added are equal to the moles of the acid neutralized. There's known information about the volume of your acid and your base. There's known information about the concentration of your base. What we don't know is the concentration of our acid, but the only way for us to determine concentration is knowing moles and knowing volume to calculate molarity. So volume is not a comparable quantity, but moles are. So at the end point of your titration, the moles of the base that you've added to your flask are equal to the moles of the acid that you've neutralized in your flask. And at this point, you should just have water. Overshot or over titrated, this would mean at this point, too much base. You've added too much extra base, so now you have a concentration of hydroxide ions that are higher than than the water that you had, which means it's going to start turning pinker and pinker. So if we model this out, first we only had hydrogen ions dissociated in solution. Then we added our base to it, which allowed us to start making water. And we still have some acid because the system hasn't turned pink yet, persisted pink. Then at the ending point, we'll only have water and we'll have our salt, but the salt doesn't matter for this part, remember? And then if you've overshot, it means you still have all that water in here, but it means that you've started now adding extra hydroxide ions in it. That's going to make your solution basic, and it's going to start turning it that pink color. Okay, so the end point of your titration, that point at which you've reached your neutral system of water, is called the equivalence point. Oops, I think it's actually, there we go, equivalence point. So if you look at the word equivalence, what word do you see? Equal. So this tells you, this is when you have your moles of base, your hydroxide, and your moles of acid, your hydrogen ions, are equal to each other. So this is the most important part. This is the really key idea behind why we can do titration calculations, is because of this fact here. So if I ask you, why are titrations allowed to work? Why are we allowed to use the calculations that I am about to show you? It is because of the point in number 7. At this point, moles of base are equal to moles of acid. Moles of base added equal to moles of acid reacted. We're doing a base to acid titration in our lab. We're doing a base to acid titration in this example, but it would be the exact same thing if you did it oppositely. If you did an acid to base titration, your moles of acid added would be equal to your moles of base neutralized. Okay, so in number 8, I'm about to walk you through the exact calculations that you need in order to solve the problem for this lab. So if you get stuck when you are doing this lab and you're like, oh shoot, I have all of this data, I don't know what to do with it now, I don't know how to work up my calculations, come back and look at number 8, please. So number 8, highlight it, star it, sleep with it under your pillow, give it a little kiss. It's your bestie for this lab. Okay, here's your example. Let's say I have some nitric acid. I use a burette and I measure out 25.04 milliliters of nitric acid into an Erlenmeyer flask. So this is my unknown, my analyte. I know my volume. I do not know my concentration of it. It is what I'm going to titrate. I then have to get myself set up to use my titrant. My titrant is going to be 0.5 molar sodium hydroxide solution. I add that to my burette all the way up to the 0 mark on my burette. Because this thing tells me I pour 100 milliliters in, it means I have a 100 milliliter burette. So if I draw you a little picture here, what this would mean is that this is the 0.00 mark and this is the 100.00 liter mark. So I filled my burette completely. I'm starting at 0. Okay. Then I begin to titrate, which means that I open up the burette and I start allowing the base to flow into the acid in my reaction flask. Eventually, the solution turns a very faint light pink because I'm a pro at titrations. Just kidding. They also stress me out. They stress everybody out. They're crazy. And then I stop titrating. The final volume that you read on the burette happens to be 48.80, it should say, milliliters. Crazy. So, first things first, how much base did the titration require? If my final reading is 48.80 milliliters, that's crazy that I put that there, is 48.80 milliliters, I have to just do a delta V calculation. My final reading is 48.8. My initial reading would be 0 because that's how much I added in. So how much base did it require? 48.80 milliliters. Yay. That's kind of the nice thing about using burettes is that you always start at 0 and then you just add in, you read your final volume, good to go. Okay. So now that I have this information, I can finally answer the question, what is the molarity or the concentration of my unlabeled nitric acid, my unknown? I know information about volume. I know information about molarity for my titrant. I know information about volume for my analyte. So now I have to find a way to put all of that together to get concentration. So here's how you're going to do it. Step 1. Wow, I'm even labeling the steps for you. I'm so nice. So, step 1. The only comparable unit we have is moles. So step 1 is to find number of moles of titrant added. So I know that I added in 48.80 milliliters. I don't know the density of this, but I have other information I can use to help me get to moles. I know volume, I know molarity. I can get moles from that, knowing that molarity is equal to moles over volume. And I can rearrange this equation to just simply solve for moles. So the molarity of my base was 0.5 molar. So 0.5 moles per liter was the molarity of my base. I know that I added in 48.80 milliliters. So now I have to multiply this by my volume, but I need my units to be the same, so I got to convert that to liters. So 0.0480 liters. Then when I solve this, my moles of OH added are equal to, putting in my calculator, I get 0.02440 moles. I'm going to try and keep as many decimals as we possibly can to make sure our answer is as accurate as it possibly can be at the end of this. Okay, so that's step 1. Now step 2. After you've found the number of moles of base that you've added, you have to think about what this actually means, right? So after you've added in that amount of base, what do you have in your reaction flask? I added in base, my system is now light pink, so I'm at this point right here. So what I've got in my solution is just water. So at the end point of my titration, remember this is the most important part, the moles of base that I've added are equal to the moles of acid that I reacted. So find number moles of acid neutralized. It seems really easy peasy, right? Oh, I added in this much base. That's how much acid I neutralized. There's only one other step that you have to think about. So at equivalence point, moles of OH are equal to moles of H plus reacted. But you do have to consider the identity of your acid and the identity of your base. We go back and we have to keep in mind the reaction equation for what's actually happening in our flask. I'm reacting nitric acid with sodium hydroxide, which you did, you wrote an equation for back in number 3 of this lab packet. At the end of this, you should have ended up with a net ionic equation of OH minus plus H plus yields H2O. Okay. This is a balanced chemical equation. So the reason why this is important is because for every 1 mole of base that you're adding in, you're going to react 1 mole of your nitric acid, which is great. The reason why I bring this up is because nitric acid is what's called a monoprotic acid. Prefix mono meaning 1, protic meaning proton. So monoprotic acids have only 1 hydrogen, which means their net ionic equation is going to result in a 1-to-1 mole ratio, which is great. But you can have other acids like sulfuric acid that are diprotic acids. Diprotic acids mean that you have 2 moles of sulfuric acid or 2 moles of hydrogen per every 1 mole of sulfuric acid, which is going to change your mole-to-mole ratio, and it's going to change your balanced chemical equation a bit. So I bring this up now. We will do another example with a diprotic acid, but for right now, we're just going to focus on the fact that this happens to be 1-to-1 because we're dealing with nitric acid here. So at equivalence point, moles of OH minus added are equal to moles of H plus reacted. So because 1-to-1 ratio, we know that 0.02440 moles of H plus, no, moles of OH minus react in this mole ratio here, leading us to have the same number of moles of acid. Okay, so now that we know this information, we can move on to step 3, our last step. We started with figuring out how much titrant we added. We converted that thing to moles. We compared our moles by knowing that at equivalence point, the moles of the acid and base reacted must be equal to each other. So final step is to take the information about the moles of our acid and calculate concentration of acid. This is our unknown. So calculate concentration of acid. We know that the formula for concentration or molarity is equal to moles over volume. Our moles, 0.02440. How much volume of our acid do we have? Well, we have to go back to our equation for that. It says, or a question for that, it says we added in 25.04 milliliters of our acid. So convert this to liters. We end up with 0.02504. And before you even think about doing math, before you even plug this into your calculator, look at those 2 numbers. They are exceptionally close together, right? Which means you should be at about 1 for your molarity because those 2 numbers are almost the same. Turns out when you plug it into your calculator, you end up with 0.9744 molar for your final concentration. This number is very, 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 very close to 1, which means it is very likely that the molarity of our acid is actually 1 molar, and we just have a little bit of experimental error in there that's causing our concentration to be slightly lower than expected. So one thing I might challenge you to think about is why would our acid concentration be slightly lower than what it actually should be? Think about how we got all the numbers we got, where they came from. See if you can kind of piece that together to have something ready to share out tomorrow when we do this lab. Okay, and then last thing, I do want to talk you through safety concerns here. I will talk them through with you tomorrow, but acids and bases that we're going to work with are in concentrations that are higher than 0.1 molar, which means we do need to concern ourselves with them. You're going to make sure that you definitely wear gloves if you're working with these things. You're going to wear goggles tomorrow. Acids and bases are corrosive. They're very strong irritants if you get them on your skin, or really bad if you get them in your eyes. So Make sure you come with your hair pulled back because you don't want your hair knocking anything over, getting in front of your eyes, spilling anything. Make sure you wear clothes that are not your nicest clothes because just in case you spill, you're going to get those on your clothes, so just be careful. And then you're going to wash your hands with soap and water before you leave the classroom tomorrow. Okay? All right. Excellent titration lecture, everybody. See you tomorrow.